Hello everyone, my name is Tasneem Safdari and in today's video I am going to explain question number 8 of end semester paper of data science. In the previous videos I have explained and we have discussed till question number 7 both parts A and B. So in today's lecture we will be discussing question number 8 both part A and B. So let's start. Compare decision tree, random forest and boosting highlighting strength and weakness of each. So decision tree. What is a decision tree? So a decision tree is a flowchart like structure that splits data based on feature values. Example, age is less than 30. So it will be yes or no. So it is like a flowchart that splits the data based on certain feature values. It continues splitting until it classifies the data. So strength, simple and easy to understand. It works like real life decision. You can visualize it like we have a root node where it says if age is less than 30, so we can directly go to yes or no. So it is like a real life decisions. And no need for feature scaling, no need for normalization or standardization. Works on both numerical and categorical data. It is very flexible. Fast and low computational cost. Training and testing are quick. Weakness of decision tree, overfitting. It learns noise from training data, creates very deep complicated trees. Unstable, small changes in data can change the entire tree. And not very accurate, single trees usually have lower accuracy. Then random forest. Random forest is a collection of many decision trees. It uses bagging. So random forest is a collection of many decision trees. Each tree receives a random subset of the data and the final prediction is equals to majority votes, that is classification, or average, which is regression. So what are the strengths of random forest? Much higher accuracy than a single decision tree, combines many trees, which in turn reduces the errors, then reduces overfitting. Ensemble of trees is more generalized, handles noisy data well, works fine even if some features are irrelevant, and good for large data sets, stable and reliable. Weakness of random forest, slower than a decision tree. Many trees means more computation, not easily interpretable. You cannot visualize 100 trees at once. And large model size, it consumes memory because we have made many we have combined many decision trees and one tree is formed, which is the random forest is formed. So it is very complicated. You cannot look at it at once, you cannot visualize it, and it consumes more memory. Now boosting builds many weak decision trees sequentially. Tree 1 learns symbol pattern. Tree 2 focuses on errors of tree 1 and tree 3 focuses on error of tree 2, and it continues, means it is so on, it goes on till end. So it builds many weak decision trees sequentially. So we have built tree 1 and tree 2 will focus on errors of tree 1. Similarly, T3 will focus on the errors of tree 2 and it will continue. Each next tree improves the previous one. Strengths of boosting, very high accuracy, one of the best ML methods for competitions. Reduces bias, focuses on mistakes and corrects them. Works well with complex patterns, can capture non-linear relationships. Weakness of boosting, sensitive to noise. Since it focuses on error, mislabeled data can mislead the model. Slower to train. Trees are built one after another sequentially, and overfitting risk it if not tuned properly. So it will overfit. So what is the summary if we see the comparison table? So decision tree, it is simple, interpretable, fast, no scaling is needed. And weakness is overfit, unstable, low accuracy. And random forest, high accuracy, reduces overfitting, stable, handles noise, low, large model, hard to interpret. And boosting, high accuracy, reduces bias, handles complex data. slowest, sensitive to noise, and risk of overfitting. So this is part A of question number 8. Question number 8 part B. Show how basic logic gates can be built using single layer neural networks like complete gate, number of neurons, activation function, and back propagation if needed. So perceptron model and activation. A single layer perceptron for two inputs, compute z equal to w1 x1 plus w2 x2 plus b and output using a step threshold activation. So we have a y function. Y stays if its answer is 1 if z is greater than equal to 0 and answer is 0 if z is less than 0. So x1, x2 are the two input bits which can be 0 or 1. So we have two input bits and w2 and w2 are their weights. And B is the bias, can be seen as W0 into 1. The line W1 is equal to 0 is the decision boundary. Points on one side, output 1, on other side, output 0. We can handle weights and bias so that the perceptron implements Boolean functions that are linearly separable. Now we have a truth table. So inputs are x1 and x2 as we have seen, and the values will be taken as 0, 0, 0, 1. It should be 0, 0, 0, 1, 1, 0 and 1, 1. So this will be the output. Actually this is 0, 1 will be 0, 0. This will be 0, 0. Oh sorry. Input is this. So 0, 0, 0, 1, 1, 0, 1, 1. Sorry. So this will be AND, OR, NAND, NOR and XOR. So output will be this respectively after applying the operation. So this will be the truth table of the particular gates. Are linearly separable, XOR is not. Now implementing AND. So desired output 1 only when 1, 1. Pick weights and biased, a common simple choice. So W1 and B equal to minus 1.5. Now we'll compute Z and Y for each input. So Z equal to 1, Y equal to 0. Then we'll compute Z equal to 0 plus 1, Y equal to this. So we'll be computing the value of Z and Y for each entries. Matches AND truth table. So when we'll match this, we'll see that it is matching the AND truth table. So geometric view decision boundary equals separates 1, 1 on positive side, others on negative. So it is implementing. Similarly, we'll implement OR. So we'll take W1 1 be equal to this, and when we'll calculate the value of respective x, z and y for the respective points, we'll find that it matches OR. So decision boundary will be this. Now implementing NAND. So NAND is negative of AND, output 0 when 1, 1. So one way flip signs of AND, weights and bias. So we'll take W1 minus 1, W2 minus 1 be equal to 1.5. So it will check. So Z will be this. So matches NAND. So it is working. So the output for Z and Y for respective points is same. So it is working. Now implementing NOR. NOR is negation of OR. So we'll put weight minus 1 and W2 minus 1. So it is negative of OR. So for OR, what we have taken as weight, we'll negate it, inverse the sign of it. So when putting this values, the value of Z and Y is this respectively, which matches NOR. Why XOR cannot be implemented by single layer perceptron? Look at XOR table. Outputs are 1 for 0, 1 and 1, 0 and 0 for... There is no single straight line in 2D input space that separate these two positive points from the two negative points. So there is not a single line, straight line, which can separate positive and negative. So this is the definition of non-linearly separable. Geometrically, if we see positive points are on opposite corners, negative are the other two corners. Any line will either include one positive with a negative or the other. You cannot separate positives from negatives with one linear boundary. Therefore, a single decision boundary perceptron cannot implement XOR. So there is not a straight line which can separate positives and negatives. That's why we cannot separate it. How to implement XOR with a multi-layer neuron? Concrete example. We need a two-layer network. Input is the hidden layer, two neurons, and output. So use step or sigmoid activation in hidden. Final output can use step. A standard construction uses hidden neurons that compute intermediate linearly separable functions, and the output neuron computes end of those. So XOR, you can see first is containing OR and second is AND, which can be formed as XOR, OR, and NAND. So network hidden neuron H1 implements OR, H2 implements NAND, and output neuron implements AND on H1 and H2. Use values like weights and bias matching earlier choice. Hidden layer will be this and this. And when we output neuron is AND on H1 and H2, we have calculated H1, H2 and then output. So this will be the answer for 0, 0. H1 is OR of 0 and H2, and output will be AND of this. And similarly OR, NAND and AND. So this will be the output. XOR equal to 0. So XOR realized by two-layer MLP. Because this requires a hidden layer, Bragg proportion is needed when weights are learned. Single layer perceptron learning is insufficient. So XOR we need two layer. Input has two layers, which is the hidden layers. Now perceptron learning. How single layer gates can be learned automatically. So the perceptron learning rule, simple form. Initialize weight. For each training example, compute output Y. Updated weights, if wrong, will be this, where N is the learning rate. So formula for WJ and B is given. For linearly separable targets like AND, OR, and NOT, the perceptron learning converges to weights that separate classes. For XOR, it will not converge. Activation choices and training note. Step, it is the classic perceptron activation. It's not differentiable. So standard gradient based backprop cannot be applied directly to a network of step units, and sigmoid activation are used in modern networks because they are differentiable and allow gradient descent propagation. Manually, we typically use step activations, but the same logical behavior can be approximated with sigmoid. And for single layer gates, learning can use perceptron rule. For multi-layer networks, we use back propagation with sigmoid. Now visual. We see here we have a gate AND, OR, NAND, NOR, and XOR. So AND, we have neural network 1, OR also contains 1, NAND 1, NOR 1, and XOR not possible with 1. We need at least 2 hidden neurons and 1 output neuron, which is multi-layered network. And here step activation function is step, step, step. Okay, threshold and hidden step sigmoid, output step sigmoid, and back proportion is not needed because it is single layer. So in single layer we do not need back proportion in OR, NAND, and NOR. And XOR, yes, we need single to learn weights for multiple layer network via backdrop or other multi-layer training. So we need back propagation. So this was all about question number 8. We have finished question number 8. This was all about the gates, activation function, and that's it. So I hope you liked it. Thank you so much for watching.